Going from a stiffness limited design to a strength limited design, we define a shape factor as the ratio of the bending strength for a shaped section to that of a reference section. In this case, it would be the same square cross section. We said the section modulus is b cubed by 6, and since the area is b square for the square section, it can be represented in terms of a as a to the power 1.5 divided by 6. So what does that mean? If you keep the area constant, what happens to the section modulus z, which is I divided by y max? So it's basically the surface stress that is seen for this at failure that is seen for this geometry. So this bending strength at the onset of plasticity is proportional to z times sigma y, which is the failure strength. And so if you normalize the bending strength for the new shape to that of the square cross-section shape, then you basically, for the same material, get the shape efficiency factor as z divided by z naught. And z naught is this term over here. If you substitute that, 6z divided by a to the power 1.5 is your shape factor, strength limited design. So we had looked last week at the fact that the material index that takes into account the choice of material, so with characteristic values of sigma and rho, if you had to then combine that with shape related attributes, you could come up with a new material index for minimizing mass. And it was given by this term. We derived that last class for this type of a geometry and loading condition. What happens when you begin to look at these materials, a spruce, bamboo, and a carbon fiber reinforced plastics? Each of them have different values of strength to failure, and all of them have different densities. So you have to minimize mass. And this is taken from a bicycle fork problem in your text. When you go from the spruce to the bamboo to the carbon fiber reinforced plastic, you have increasing shape factors. If you initially looked at minimizing mass without taking into account shape variations, you would use this term over here, the failure strength raised to 2 power 3 divided by rho as the material index for minimizing mass. Let us calculate the material index in each situation for these three materials, right? In the first case, when you don't take into account shape, you have a material index of 36. And when you go from spruce to bamboo, check to see if the material index is now 35. And for carbon fiber reinforced plastics, it's 35, right? So these are all pretty much equivalent numbers in these three cases. But because of the shape factor differences, the modified material index we had derived last week as a material index where you would have, instead of sigma f to the power 2 by 3, you would have the shape factor phi times sigma f under this index of 2 power 3. So now with this new equation, if you were to take into account shape factors, what do you get? In the first case, phi is 1, and so you get the same shape efficiency factor. And then as this shape efficiency factor doubles roughly, this is about square root of 2 times. And so same thing, if as it quadruples, it's almost 3 times that amount. So this gives an idea of the fact that different materials can be created into shapes without buckling to greater extents. What happens when you look at 4 other materials that are, one is steel, and the other 3 are lower density materials: aluminum, titanium, magnesium, which are used in engineering structures. Steel, of course, has the virtue of having a much higher failure strength, but also a much higher, the highest density. Suppose you had these values of shape factors for this particular case to failure. I will leave it as an exercise for you to determine what the material indices are in this case. So when you don't include shape factors, the best choice is this spruce, this Norwegian spruce, okay, because it has the highest material index without taking into account any shape variations. And this can be seen in this with the rest of the math over here. If it turns out that you begin to take into account shape efficiency factors to failure for these designs, you end up having much more attractive choices. Carbon fiber reinforced plastics in particular end up becoming the best choice, taking into account not only the fact that the efficiency factor is higher, but density is also not increased as much as it is for steel or titanium, for instance. This can be explored graphically as well if you plotted sigma versus rho with the right choice of units on CES EduPack, and you were able to use a slope of a line. The slope of the line would be 3 over 2, and it would pass through a specific point. Let us say it passes through one type of an oak, because we may not have a Norwegian spruce in the database, for instance. You begin to see what were some of the competitive materials hovering around this vicinity, and the fact that you could go from a steel that was poorly shaped to a steel that was more effectively shaped into a useful structure, to move it from something that was completely out of the reckoning to something that was more competitive. And then similarly for aluminum and so on, and for carbon fiber reinforced plastics will be right there anyway, right? So you get a chance to see how before, you had a chance based on shape efficiency factor differences that CFRP was very close, but as you increased or varied the shape, you could end up getting a better choice. This was for steel, and basically you're effectively looking for a new material that had an effective strength of sigma over phi square and an effective density of sigma or rho over phi square. So if you begin to look at this in comparison on CES EduPack, you will be able to explore this analysis in the same way that you did by numerically calculating this on an Excel spreadsheet for reference, or by pen and paper to get a feel for what's happening. In the next class, we will look at how to be able to graphically solve these problems to get the right material section. Now we've seen that you can calculate the mass of a beam by this term over here, where you begin to take into account the shape efficiency factor for bending strength. So you can choose materials with the largest value of this material index. There are ways to be able to empirically, so that is experimentally, calculate the shape efficiency factor for various situations by rearranging terms, where if you move phi f over here and you know all the other attributes based on the load, the mass, the dimensions, and the material, you can estimate what is the value of phi f for real life situations. It can be anything from a bridge, which is a very complicated structure, compared to this small I-beam over here.